Hello, Calculus. We'll be viewing this edition after class on Friday, which is the 30th, last day of the month already. So don't blink or the whole year will be gone. Well, it's sort of a theoretical lesson, so we're going to look at continuity again and pairing with it differentiability. Differentiability. All right, so that's a mouthful, but I think you can handle it. Can you see that? All right, somewhere in the middle there. It looks good. All right, to use, we're going to use the alternative form of a derivative that you saw one time, where we took f prime at x and we defined it as the limit as x approaches some value c of f of x minus f of c over x minus c. Oops, c. So let me go ahead and remind you how the picture bears this up. It was another way of thinking of finding the slope of a tangent. Say we want the tangent right there. So it's going to be the slope of that line. But initially, we can't get that, so we start with the secant. And we just set up our values a little differently. We had a c value here, and we called this an x value. So therefore, this was f of c, and this was f of x. So we get the slope of the triangle, which is the slope of the secant, is f of x minus f of c is this distance, and x minus c is that distance. So when we put one over top of the other, we would have the slope, f of x minus f of c over x minus c. And we're going to have the x value move closer. So the x value is here, then it gets closer to the tangent, and here, and finally approaching it, we are at the tangent line. So we take the limit as x approaches c. And that was our alternative definition of the derivative. So just another way of setting up. Same idea behind it. All right, so we're going to use that in our definition today. And we're going to use it to define one-sided derivatives. We've looked at one-sided limits. So since a derivative is a limit, it should be okay with you if we look at it that way. So if I look at the limit as x approaches c, say from the left, of f of x minus f of c over x minus c, that will be the derivative from the left. And so go ahead and write what you think the derivative from the right looks like. So it should be very similar. We're approaching c just from the right side, indicated by the plus sign, and the same expression. All right, so we're going to look at a limit, a derivative from the left, and a derivative from the right. The reason we need that is to define we're going to define a closed interval for differentiability. So we're going to say a function f is differentiable on the closed interval a, b. So remember, the brackets mean it's closed in that it will include a and include b and everything in between. So that's interval notation for a closed interval, as opposed to an open interval, which does not include the endpoints a and b, but everything in between. So in this definition, we're defining differentiability on a closed interval. So it's going to be differentiable on this closed interval if it is differentiable on the closed interval. So that is going to include everything but the endpoints. And for it to be differentiable on the closed one, it's going to be differentiable on the open one, which is everything but A and B. So now we have to address A and B. And if there exists a derivative from the left at which point? It's going to be at this point or this point. So in order for this whole thing, including the endpoints, to be differentiable, everything in between on the open interval is differentiable. And if there exists a derivative from the left, if we're coming in from the left, then it would have to be at point B. And from the right at A. So a little sketch might help. So any function, here's my A, here's my B. Let's say this function stops right there. And as we're approaching, we want to know if it's differentiable on this whole section, including A and B. It's this whole interval. So we decided, well, it's going to be called differentiable if every point inside is differentiable, which means it has a slope to its tangent anywhere. And then right when we get to the endpoint, we can't really draw a slope at the endpoint because we don't know what the tangent would look like. So which of those values would it be? So therefore, we just look at one side. We're going to look at the derivative from the left at B, and we're not going to care about all the other side's possibilities. So as we're getting closer and closer to B, we're going to look at the tangents that create slopes on that side only. And we're coming to A. Our slopes are going to be getting closer and closer to A, never reaching A, but getting closer and closer. As we come in from the right at A, we are creating points that have tangents that we can find the slopes of. But if we include A, then we don't know exactly what the tangent would look like. So therefore, we address this problem by coming in from the right at A and from the left at B. So we're defined what something is differentiable. In more useful thinking, a function, say it's got a hole in the bottom of the sea here. I can draw a tangent and find its slope at those points. But what about at this point right here? Say this is point C. When there's an opening like that, there's no way I know which way to draw my tangent line. So therefore, I can't come up with a slope. So there's no derivative at a hole like that. What about when there's a jump? So here and here. What are your thoughts about that? Is there a derivative at C? Can I draw a point at C and draw a, here's the value. Can I draw a tangent there? No, I don't know which way to draw it. So there's no derivative at C. What about when it's asymptotic? Say it's C is an asymptote and it goes, say, up like this. Can I get a slope here at C? No, the graph never reaches C, so how can I draw a tangent line at C? All right, so these, you'll notice, are not continuous. So what is the connection between continuity and differentiability? So let's make some, remember in layman's terms, a graph is continuous if I can draw it without lifting my pen. So these are all three not continuous. And a derivative means I can draw a point and get a slope at that point to the tangent of the tangent at that point. So putting those two together on next part, we will decide the relationship between continuity and differentiability. So till part 2.